Hello. All right, we're going to do section 5.5 of James Stewart's calculus. He has two different versions of the book. I'm going to be using the one that has the early transcendental words in the title. So look for that one. I put a link there so you can get the book yourself, a PDF. Okay, so I decided to start with this section. This is sort of my pilot because it's my first live stream. And I just thought it'd be a good one to do because it's a little less theoretical, more practical, and it's a good way for me to introduce myself to you guys. Okay, so it's about the substitution rule. And that rule is a little misleading because chapter 5 of this book is about the antiderivative, and the antiderivative is about undoing the derivative, finding a function so that when you take the derivative, you get back to the original one. So here's the idea, that we start off with a function, f of x, and the symbolism that we use is this, it's like an S, like a big S for summative of this function. So it's a new function. If you took the derivative of f of x, you would get back to the original little f of x. Okay, and so we already know some derivatives, and so those are going to, the ones that we know the derivatives of, it's easy to find the antiderivatives. So as an example, we know the easiest derivative in the history of the world is the derivative of e to the x. E to the x prime is e to the x. Okay, so guess what the antiderivative of e to the x is? Well, it's e to the x, because e to the x is the thing whose derivative gets you back to e to the x. So since we know this one, and it's very simple, it's a good one to start to illustrate the substitution rule. So since we know this, this is from previous chapters when you were studying the derivative. So now we're switching over to the antiderivative, and the integral of e to the x dx, well, looking for the thing whose derivative gets you back to e to the x. So that would be e to the x. Now, if we want the most general antiderivative, we can always add a constant, because remember, when you take the derivative of a constant, you get 0. So if I were to take the derivative of e to the x plus c, I would get the derivative of e to the x plus the derivative of c, which is, this part is e to the x, and this part is 0, so I get back to e to the x. So there is this thing right here is the most general antiderivative for e to the x. Okay, so now we're going to build on that. Okay, hopefully that was straightforward, because that's why we're using e to the x in the first place. Now we're going to switch it. Now get ready, because it's a big leap. We're now going to study e to the u du. Well, I've made a big change here. I've made the x now a u, and guess what? It doesn't change much. The antiderivative of e to the u is also e to the u plus c. I don't need to go check it because I just changed the symbolism. Now, the reason we use this is, well, it's traditional, but in your book uses it, so that's important. We're going to try to follow what they do. But knowing this right here allows us to do things like e to the 2x dx. So I want to know the thing whose derivative is e to the 2x. That's what this symbolism means. This means find me the function so that when I take the derivative of that function, I get back to e to the 2x. So what we do is we say, well, I'm really good at this one, and this one looks a little different. So what I'm going to do is I'm going to try to change it into something that I'm good at. So I'm going to say, well, I'd rather this 2x not be 2x. I'd rather it be u. So I'm going to let u equal 2x. Okay, now I have to convert into an integral that looks like this, but I need to account for everything in this integral because that's the integral that was presented to me. I cannot change the problem that was given to me. All right, so I'm going to let u equal 2x. And what I need to do is I need to get this du involved, and I need to find out what dx was. And the way we do that is we take the derivative of this. On the left side, we get du. It's like 1 times du. The derivative of u is 1, and then you have a little du attached to it. And then this is implicit differentiation, if you remember what that is. And then on the right-hand side, I have the derivative of 2x, which is 2, and then we put in the dx, because, again, we're doing implicit differentiation. Okay, now if I want to account for everything I see in this integral, then I already accounted for the 2x. That's going to be u. Okay, so so this guy is going to become e to the u. And what was dx? The dx is du over 2. So if I want to convert this if I'm converting this integral into a u integral, then the e to the 2x part is e to the u, and the dx is du over 2. That's a little clumsy with the way we've written it, so what we do is we take that 1/2 and we put it out in front, and then we have e to the u. du. And that integral I know how to do. Okay, so this is 1/2 times the integral. This part right here is well known to me, right? That's just e to the u plus a constant, if you like. Now, if I want to be real, let's just, in case somebody's following along, going, wait a second, time out. It's 1/2 times the whole thing. So let's do it. Let's do it properly. Let's explain how that works. So I have 1/2 times the integral that I know, right, which is integral of e to the u du. That's e to the u plus c. So technically I have 1/2 times that. And then what I do, and we don't really do this step, but just to let you know where it went. So I have 1/2 times a constant. Well, that's just another constant, so we'll just call it a constant. Okay, so what I've determined is that the antiderivative of e to the 2x is equal to 1/2 e to the 2x plus c. Now let's go check that. Okay, so remember, if you have, just remembering our derivatives, if you have e to the Mickey Mouse prime, then you get e to the Mickey Mouse back again times e times Mickey Mouse prime. Times Mickey Mouse prime. Okay, so in our case, the Mickey Mouse is 2x, so I have e to the 2x prime equals, well, it says, here's my decoder ring, e to the Mickey Mouse is e to the Mickey Mouse back again, so that means I must get e to the 2x back again, and then I'm supposed to go times the Mickey Mouse prime. In this case, 2x is my Mickey Mouse, so the derivative of 2x is 2, so I get 2e to the 2x. Okay, now if I had a 1/2 out in front, right, 1/2 out in front, then I'd have another 1/2, and I'd have another 1/2, and I would get e to the 2x. Okay, so you see that when I do take the derivative of 1/2 e to the 2x, I do get back to e to the 2x. Okay, that's our first example. A lot of explanation needed. This is my first time with you people, and also it's the first example. Okay, let's build on that. Okay, so the idea is that we know we're really good at e to the u du. I mean, we are world experts at e to the u du. And so since that's what we're good at, we really hope that the problems that are presented to us can be put into that form. And at this stage in the book, there's little exceptions, little tweaks, little ways that we try to confuse the enemy. But in general, in this section of the book, when you see an e, you're probably going to have to convert it into e to the u du. that's what you hope for, because this is really easy to do. Okay, so let's see another example. Let's say I have the integral of x e to the x squared dx. Now, this looks intimidating, right? When have you ever seen e to the x squared? When have you ever seen an x attached to it? Well, it's intimidating looking, but you have to say to yourself, what I would love for this to just be is e to the u. And the only way it's ever going to be e to the u is if I let this x squared part be u. So let's start with that. We'll say, let u equal x squared. Now, if you look back at what we did in the previous example, as soon as I let u equal something, the first thing I did was take the derivative of each side. So I'm going to do that here. Okay, let u equal x squared, and then I'm going to do du is 2x dx. Okay, now what I need to do is I need to account for everything in this integral. All right, now the e to the x squared, that's going to be easy because that's u, right? That's e to the u. So this guy is going to become, I'm going to get e to the u there. Now what about the x dx? I haven't accounted for that yet, but it's right here. Here's that x dx. So x dx equals 1/2 du. All right, well, that's great because that means this integral converts into 1/2 e to the u du. The x dx part, that is 1/2 du. And the e to the x squared part is e to the u. I've made all the substitutions. But this is the integral that I'm so good at. So this is 1/2 e to the u plus c. But then we have to put it back the way we found it, right? U is not the way the problem was presented to us. It was presented to us in x. So let's go back and put it the way we found it. We found it where u is equal to x squared. Okay, and then we can go double check and make sure that that is, in fact, the antiderivative of x e to the x squared. How do we do that? Well, we take the derivative of it. Okay, this is our antiderivative. So if I take the derivative of this, I get 1/2 e to the x squared prime. Remember, we can just take the constants out in front and just take the derivative of the function part. Constants come along for the ride. And then plus c prime. This is always 0. Okay, now what do we do here? It's e to the Mickey Mouse. So I get e to the Mickey Mouse back again times the derivative of x squared, which is 2x. And when I reduce this, I just get x e to the x squared. Okay, so just recap. We started wanting to know what is the thing whose derivative is x e to the x squared. And we found this to be the answer. Then we went and double checked it, took the derivative of it, and we did in fact get back to e to the x squared, x e to the x squared. Okay, so those are good examples with e to the x. Let's keep going with e to the x just because it gets us, in the flow of reminding ourselves what some derivatives are and things. So let's put some trig functions in here. Let's say I had this real intimidating type thing, cosine x e to the sine x dx. Wow. Well, that sure is intimidating. Somebody went out of their way to really try to confuse me. However, what I say to myself is, hey, I'm only good at e to the u. So I might as well make that sine x here u, so at least I got e to the u, and let's see if we can work it out from there. So we'll let u equal sine x. And remember, as soon as you do that, you're going to take the derivative of whatever you picked for u. So on the left-hand side, you get du. Remember, that's 1 times du using implicit differentiation. And then the derivative of sine x is cosine x dx. Okay, let's see if we can account for everything we can, everything that's presented in this integral, because after all, we can't change the problem, but we can convert it into something that's a little bit more palatable. e to the sine x, well, that's going to be e to the u. That's the thing I'm good at. And then cosine x dx is still left over to be accounted for. But look, cosine x dx, well, that's just equal to du. So that integral, this integral here, converts perfectly into e to the u du, which is the one I'm so good at. I know that's e to the u plus c. Then I have to put things back the way I found them. I'm the one who decided that u is equal to sine x, so let's go back and put in sine x for u, and there's our answer. Again, we can check. If I take the derivative of e to the sine x, what I'm hoping to find is that I get back to this original function, right? That was our goal, to find the antiderivative of that. Well, what's the derivative here? It's e to the Mickey Mouse, you get that back again, times the derivative of Mickey Mouse. Well, in this case, Mickey Mouse is sine x. Okay, well, what's the derivative of sine x? It's cosine x. So I get e to the sine x. N would be n times x to the n plus n minus 1. Okay, well, we're in the business of doing antiderivatives, not derivatives right now. And so it's a good opportunity to really see what the antiderivative is. I would like to know what the antiderivative of x to the n is. Well, I need the thing whose derivative is x to the n. That means I need to have, because I'm always going to subtract 1 from the exponent when I take the derivative, I better have one more so that when I take preemptive strike to have the n plus 1 in the denominator so that I don't have that extra term. Now, we have to be careful because whenever we have a denominator, we have to look out for it being 0. And so we do have to qualify this and say that n is not equal to -1. And so we do have an exception when n equals -1, which I'll address in a bit. So let's take a look at this. The antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. Now, I'm going to make a big change. What if it was u to the n du? Uh-oh. Well, I think then it might be u to the n plus 1 over n plus 1. Not a big leap there, I think. Okay, so let's say that this is the integral that you're really good at. I mean, just like a world expert. So the antiderivative of, let's say, x cubed, or you say u cubed, we know that because we're world experts at that. That is u to the 4th over 4 plus c. Okay, so but you're never given that problem, right? That's too easy. But you might be given this. You might be given x times 1 plus x squared cubed dx. Okay, well, one thing you could do plus x squared. And that's simply because I'm going to stop streaming because I think I want to check and see if it's still working. And this is my pilot program. So I'm going to stop streaming because I just got a notification that